All matter is composed of basic building blocks called atoms. Um, Atom is so small that it cannot be seen even with the most powerful light microscope. Atom is made up of three subatomic particles: electrons, protons, and neutrons. The central part of the atom is known as nucleus, and the protons and neutrons are in the nucleus, and the electrons are revolving around the nucleus in different energy levels known as principal energy levels. Protons Protons are positively charged, electrons are negatively charged, and neutrons have no charge. Atom is neutral. What does that mean? That the number of protons, they are equal to number of electrons in an atom. If you look at the symbol of an element, there are different ways the symbol of the elements can be represented with the atomic number and mass number. For example, if an element is written, let's say chlorine, and let's say these two numbers are written like this. This is subscript, this is superscript, and on the left side. Then this is known as the atomic number of an atom, and this is known as the mass number. What does atomic number means? Atomic number, which is represented by the letter Z, is the number of protons. That means an atom of chlorine, one atom of chlorine has 17 protons. Then how many electrons will be there? Since protons and electrons are equal in number, that means there will be 17 electrons. Then the number here, this 35, is known as the mass number, which is denoted by the letter A. That mass number is number of protons plus number of neutrons. So this is mass number, protons plus neutrons, and this atomic number is protons. So if you have to find the number of neutrons, all you have to do is mass number minus atomic number. So 35 minus 17, which will be 18. So an atom of chlorine has 17 protons, 17 electrons, and 18 neutrons. Now, we have seen in the previous video that there is a reason that elements are classified into groups and periods. So if you have, for example, element in the first A group, all these elements' chemical properties are similar. And why they are similar? Because they all have the same number of electrons present in the outermost shell. The elements in the first A group have one electron in the outermost shell. Elements in the second A group has two electrons in the outermost shell. Third A group, 3 electrons in the outermost shell, and so on. So if the elements in the group have similar chemical properties and they have the same number of electrons in the outermost shell, that means we can say that the number of electrons in the outermost shell are somehow linked to the chemical properties of an element. Since the number of protons are equal to the number of electrons, that means we have to look at the atomic number to find the number of protons, number of electrons for an atom. Now in this periodic table, if you look, for example, it's written like this. Let me make it lithium. If you see, it says 3 here and 7 here. Now you're going to say, why in this one atomic number is written on the top? So that's another abbreviation. But of course, your atomic number is going to be smaller than the mass number, because atomic number is just the number of protons. So lithium basically has atomic number is 3. That means 3 protons. 3 protons means 3 electrons. Then we want to find out where those 3 electrons are. Um, so here, as we discussed, that let's say this is the nucleus and the electrons are revolving in different energy levels. This first one is known as first energy level, second energy level, third energy level, and so on. First, second, third, fourth, fifth, sixth, seventh. If the electron is in the first energy level, then there can let me write it down. These energy levels are further subdivided into sublevels. First energy level is subdivided into one sublevel, we call it as 1s. Second energy level is divided into two sublevels and their names are 2s and 2p. Third energy level divided into three sublevels, we call them as 3s, 3p, 3d. Fourth energy level, four sublevels, call them as 4s, 4p, 4d, 4f. Then fifth and so on, we can keep writing 5d, f, 6s, 6p, 6d. Here. Now electrons love to stay close to the nucleus because nucleus has protons positively charged, electrons negatively charged, so opposite charges attract each other. So we always fill the lower energy level first, followed by the higher energy level. So this is the lowest energy level, 1s. So you fill this first. Once this is full, then you go to 2s. When 2s is full, you go to 2p, then 3s. So you just follow the arrows, then you fill 3p, then 4s, 3d, 4p, 4s, and so on. If you see the letter S in the sublevel, you can put maximum 2 electrons here. It's like an apartment with the address S. So if the address of an apartment says S, means only 2 people can stay there. If you see P in the sublevel, P sublevel you can fill 6, D sublevel you can put 10, F sublevel you can put 14, and so on. So when you're filling these sublevels, remember we said we're going to fill 1s first, then 2s, then 2p, then 3s, then 3p. After 3p is 4s, then 4p. Oh, sorry, after 4s is 3d. Sorry. Now, isn't it interesting that we are saying that 4s, fourth energy level, this sublevel is lower in energy than 3d, even though 3 means third energy level. Yes, it also depends on the orientation of these sublevels. And yes, 4s is lower in energy than 3d, so we're going to fill that first. And then after 4s was 3d, after 3d is 4p, after 4p is 5s, and so on. So for example, lithium atomic number is 3. So what will be its electronic configuration? Your first 2 electrons will go here. Remember, S can have maximum 2. How many are left? 1. So 1 here. That means lithium electronic configuration is 1s2, 2s1. Let's look at the next example. Fluorine. Fluorine is here. Fluorine atomic number is 9. So 9 electrons. So let's start filling. 1s2, 2s2. We have 9, so we already filled 4. 9 minus 4 is 5. So 2p5. So electronic configuration is 1s2, 2s2, 2p5. Then bromine. Now here's the thing, bromine is here, right here, 35 electrons. So now when I'm filling 35 electrons, this is the way I'm going to do it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Count it. 2 plus 2, 4, 6, 10, 12, 18, plus 2, 20, 30, and 35. That's electronic configuration of bromine. All I'm doing is if I see S, I put 2, if I see P, I see 6, D10, and F is 14, and then I'm just following these arrows. And this is known as Aufbau's principle. What does Aufbau's principle means? That lower energy levels are filled first, followed by the higher energy levels. Energy levels are filled first. And why they are lower in energy? Because of the attraction with the nucleus. Now, truly speaking, class, you're gonna try barium. I'm gonna pause it. You're gonna try barium, and then I'm going to write it down, and then you can see the answer. And here is your electronic configuration for barium. Now, truly speaking, class, you really do not even have to look at this whole Aufbau's principle and follow this. There is a very short way to write down the electronic configuration too, just by looking at the periodic table, and the periodic table will be provided to you in the test. So all you have to look at the periodic table, and we already discussed it in the previous video, that these two columns, they are S block, all these are P block, except this helium, that is S. Then these in the middle are D block, and the two separate rows here, they are F blocks. So, and these are the rows, first, second, third, fourth, fifth, sixth, seventh. These are the rows. So if you have to, let's say, write down the electronic configuration of hydrogen, you're going to say it's in the first row, 1, and it's S block, 1s, and it's the first one, 1s1. This is also S block, 1s, 1, 2, 1s2. Let's look at this lithium. For lithium, what you're going to do, you're going to start from here, 1s2, 1s2. Now you're in the second row, 2s1, because the first one. Then what will be for beryllium? 1s2, 2s, now it's the second one, 2. Let's go to boron. Start from here, 1s2, this and this, 2s2, and now you are entering P block. So 1s2, 2s2, you're still in the second row, P1. Carbon will be 1s2, 2s2, 2p2. What will be fluorine? 1s2, 2s2, 2p5. So this is the shortcut. You can just look at the periodic table and write down the electronic configuration. Now, we said that the elements have the similar chemical properties to the elements present in the outermost shell. So if the chemical properties can be explained by looking at the electrons in the outermost shell, which are known as the valence electrons, then why do we have to write down the big, huge electronic configurations? For example, for barium, what we were writing, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. This is the outermost. If all the chemical properties can be explained just by looking at this, then why do I need all this? They are all full and they are not participating in the bond formation or any type of reaction or any type of like explaining any chemical property. And that is true. Here you're going to learn to write down the noble gas electronic configuration, which is also known as the abbreviated electronic configuration, where we will be showing only mainly the electrons present in the outermost shell. So, for example, let's say if I want to write down the electronic configuration for lithium, then what will that be? Lithium atomic number is 3 protons. So here's lithium. You look at the noble gas present before this element, closer and before. So the noble gas present before is helium. You write down the noble gas in the square bracket. So that means now you are here and you want to come here. So you write down helium and then 2s1. For example, you want to write down electronic configuration for magnesium. Magnesium atomic number is 12. What's the noble gas present close to magnesium but before magnesium? That is neon. So you write down neon. So now you are here. You explained how 10 electrons are arranged. The only thing you have to do is you have to come from neon to magnesium. So it's third row, 3s, these are s block, 1, 2. If you write on the full electronic configuration for neon, then it is 1s2, 2s2, 2p6, 3s2. So what we are saying is, and noble gases, they all have complete shells, full shells. So what we are saying here in magnesium electronic configuration, that okay, the first 10 electrons are like neon configuration and here are my outermost. This makes it very easy. If you have to write down the electronic configuration for barium, then you pick the noble gas close to the barium but before it, which is xenon, you write down xenon, and then here is the sixth row, 6s1, 2, 6s2. So let's try bromine electronic configuration. So bromine is electron 35, but we're not going to look at not writing the whole. So the noble gas present close and before is argon here. So for bromine, I'm going to start with argon. So I'm here at argon and I have to go to bromine. How will I go? Here argon. And this is my argon. Argon here. And let me use a light color pen. Argon. So now I'm here. This is my fourth row, 2s. So argon, 4s2. Now these are D. When you enter the D block, you put one less row number. If it is fourth row, then it will be one less row number is D. 3D, how many are there? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now you are entering P again. So it will be 1, 2, 3, 4, 5. With P, your number will stay same. 4P, 5. So let's try these ones. I'm going to pause the video and you try these and then we're going to discuss them. Alright, so here are cobalt, tellurium and radium electronic configurations. Please match them with your answers and let me know if you have any question. Now let's look at this question first here. If the electronic configuration is given to you, it is very easy to write down which element is denoted by that electronic configuration. And class, you do not even have to count the total number of electrons. You look at the outermost, is like there is 3p4. So you go into the first, second, third row, and these are the p1s. So 1 2 3 4, 3p4 will be sulfur. So third row, p block, the fourth one. Similarly, look here, outermost 5s1. So this is my 1 2 3 4 5. This is my fifth row. S is S1. These are S block, and that's the first one. So it is going to be rubidium. Then look at this outermost. When I'm using the word outermost, that basically means this number. 5 means the fifth energy level. So I'm in the fifth row, 1 2 3 4 5, and then I'm in the p block. In the fifth row, where are the p blocks? Because these are S, these are D, and this is P. And the third one, 5p3, 1 2 3. So that is antimony. Now let's go to this interesting one, the outermost. Is it 5d6 or is it 6s2? It is 6. 6 is the outermost energy level. But look here, this is the way we're going to do it. 6s2. This is the 6s2. This here. Remember, if you are looking at the outermost 5d6, for the D we put one less row number. If for D we put one less row number, that means you're gonna go in the sixth row. You're going to go in the sixth row, 1 2 3 4 5 6, and because here is going to be your D. So let's look at like this. 6s2, this is a sixth row. 6s2, why is this coming out so huge? 6s2, when we enter D block, we put one less row number. Similarly, when we enter F block, we put two less row numbers. Very interesting. If you look here, this in the sixth row here, this is 6s2, and then after that we are coming here to fill the F block, and we fill all F, and then we go back to 5D. So if we are putting one less row number for D, then for F we're going to put two less row numbers. So 6s2, 4f14, 5d6, 1 2 3 4 5 6 osmium, according to this electronic periodic table. Let's look at this. 7s2, after 7s, I should have used the different periodic table for this exercise, but let's just use this one. In the exam, I'm not going to give you the electron elements where there is some sort of anomalies between the different books. 7s2, after 7s2, we are entering this F block. 7 minus 2 is 5. This is 5F, this is 4F. 5F11, 1 2 3 4 5 6 7 8 9 10 11. 1 2 3 4 5 6 7 8 9 10 11. It should be not be this, it should be ES. I think I need to use to explain the F block elements class. There are sometimes different anomalies here where there are some gaps. This is I'm gonna write down based on this is gonna be FM, but again, um, in the exam or in the homework, you will be given only those where no matter what book or what you're using, it's all same. Going back to these configurations, so chromium, copper, and silver. So here is chromium. Chromium is here, copper is here, and silver is here. So here's the another rule, that if you're filling the electronic configurations and in the outermost if you get D4 or D9, then you make one electron jump to give it D5 or D10, because D5 or D10 half filled or fully filled D orbitals are very stable. So chromium is here, you will say argon 4s2 3d4. But then how many electrons are in D4? So what happens, one electron jumps from 4s to 3d to give argon 4s1 3d5. Why? Because if you have 5 electrons in D or 10 electrons in D, then that D orbital is very stable. Copper here, it is argon 4s2 3d9. But instead of writing argon 4s2 3d9, we're going to write down 4s1 3d10. Silver is here, krypton, what is that, 6s2, give me 1 second, I don't think it's, here is silver, so 1 2 5, 5s2 and 4d9. So what will it be? Krypton 5s1 4d10. This rule is only for when you have 4 or 9 in D and then you jump them from 4s. Last, on this slide, so let's go here and I'm going to write down the full configurations. Full configuration means not the abbreviated one. For nitrogen, atomic number is 7. It is 1s2, 2s2, 2p5. If you want to write down the abbreviated one, it is going to be helium 2s2, 2p5. So this is called the orbital diagram. What orbital diagram means, if you have S, you can put 2 electrons, we said, and if we have P, we can put 6 electrons. Remember, maximum. Why? Because each sublevel, for example S sublevel, is divided into, further subdivided into one orbital. Think about one box, and if we are using the word orbital, that means in that orbital you can put 2 electrons. So S sublevel divided into, further subdivided into one orbital, and in that one you can put 2 electrons. So here is my 1s orbital and I can put 2 electrons. I'm showing electrons with arrow, and when you put electrons in an orbital, then make sure electrons behave like a magnet. So when they have spin, so you put one upwards, one downwards to avoid the repulsion. This is known as Pauli's exclusion principle, that when you are filling 2 electrons in the same orbital, then they must have the opposite spin. So then 1s2, then 2s2. Remember p sublevel, where we can put maximum 6 electrons. That p sublevel is made up of 3 orbitals. 1, 2, 3, and in each orbital you can put 6. In each orbital you can put 2, so the total 6. So this is 2p sublevel made up of 3 orbitals, and in each you can fill 2. But when you so how many do I have? I have only 5. So when I'm filling the electrons, first I will place 1 in each orbital, and then I will start pairing up. So I have 5, so I have filled 1, 2, 3, and now I can start pairing up. This is known as Hund's rule of maximum multiplicity, is that you first fill into separate orbitals and then you start pairing them. So this is the full electronic configuration, this is the abbreviated electronic configuration, and this is the orbital diagram for nitrogen. So let's fill these two. Let me pause the video. Alright class, so here I made a mistake. Atomic number is 7. 2 plus 2, 4 plus 3, 7. It is 2p3. That means when I'm filling this up here, it should be 1s2, 2s2, 2p3. So this is oxygen, 1s2, 2s2, 2p4. So 1s2, 2s2, 2p4, 1, 2, 3, 4. Then the abbreviated one will be helium, 2s2, 2p4. Let's go to nickel. The nickel atomic number is 28. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d8. And how will I fill 8? 1, 2, 3, 4, 5, 6, 7, 8. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8.